Okay, so in the first lecture, I talked about the road to the Higgs discovery, and yesterday I talked about where we are with characterizing the properties of this new particle. And today I want to discuss, to a greater extent, what else is there after the discovery of this particle. In particular, as you can tell from my T-shirt, I'm a fan of supersymmetry. And I'll talk a little bit about prospects for possible future accelerators. And if I have time, I will also talk about the connection with a past accelerator, namely the Big Bang, through ideas of cosmological inflation, whether cosmological inflation could have been caused either by a Higgs boson or by some sort of supersymmetric theory. So I remind you of this sort of general perspective on models of Electroweak symmetry breaking that I discussed yesterday. So on my left, we have elementary Higgs people, where the elementary Higgs boson is accompanied by supersymmetry in order to protect the hierarchy of particle masses. Sorry? Oh, Skype. Okay, so then on my right side, we have the composite people who think by analogy with QCD, think by analogy with superconductivity, and imagine there is some composite order parameter which is controlling Electroweak symmetry breaking. So there is no experimental evidence for any of this, right? No evidence for supersymmetry, no evidence for composite models, no deviations from the standard model Higgs boson properties. Which, of course, makes it even more fun. I mean, if we knew which way we were going, then we would go that direction. But as it is, we can explore all sorts of different possibilities. So the fact that no new physics beyond the Higgs has shown up so far at the LHC, I think it's fair to say, has caused a fairly high degree of mortality amongst theorists. Not amongst theorists, but amongst theories. For example, people who a few years ago were advocating Higgs-less models, I think, have changed their tune. There's one or two intriguing aspects of the data as we have them at the moment. So one is the fact that we seem to be in this unstable region in the M-Higgs, M-top parameter space. But it's intriguing that actually we're very close to this stability bound. So the fact that we seem to be in the unstable region, as I argued yesterday, I think is evidence that we need some sort of new physics. But where that new physics comes in, it could be as high as 10 to the 10 GeV. Some people also remark upon the fact that the cosmological constant, the vacuum energy, the dark energy that's been observed, is close also to the bound that makes life possible. I won't discuss that. So there's a number of different theoretical responses to this. So some people, like me, like you, like supersymmetry, but they say, well, since we haven't seen it yet, maybe all or at least some of the supersymmetric particles are very heavy. So if they were 10 to the 10 GeV, that would still be probably good enough to prevent the instability in the vacuum. Or maybe the supersymmetric particle spectrum is split. Some particles are low, some particles are very heavy. Some people are much more radical. They say, well, maybe we shouldn't care about those quadratic divergences. Maybe we shouldn't care about naturalness. Maybe the laws of physics are just so. And some people even invoke the A word. Now, I don't like the A word, and I will not utter the A word. Right? Some people sort of justify that by saying, well, in string theory, you've got this tremendous landscape of possibilities, and we just happen to live in the one out of those 10 to the 500 or whatever they are consistent string theories, which gives you a cosmological constant close to Weinberg's limit, and which gives you a Higgs weighing 125.6 GeV. To me, that is close to being an abdication of our scientific responsibility. So as I said, people are sort of disappointed by the fact that supersymmetry has not shown up yet. On the other hand, my point of view is that supersymmetry anywhere would be better than nowhere. Anywhere below, let's say, the Guth scale or the Planck scale would help you sort of make the theories at least somewhat more natural. Of course, although I am an advocate of supersymmetry, supersymmetry can never explain the origin of the mass hierarchy. The best that it can do is to stabilize the hierarchy to some extent. So supersymmetry is not the last idea that we're going to need. So as I said, some people, I think, are getting a little bit carried away, saying, well, maybe there is nothing beyond the Higgs. They say maybe the theory is consistent, that's just the way that things are. This, I think, is absurdly hubristic. And let me remind you of physicists in the past who have thought that they had completed physics. Michelson: the more important fundamental laws and facts of physical science have all been discovered. 1894. Just before the discovery of the electron, quantum physics, relativity, and so on. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. Lord Kelvin, 1900. Just to show that hubris is a transatlantic phenomenon. Is the end in sight for theoretical physics? Stephen Hawking, 1980. But let me now give you my favorite example, which actually is not from the world of physics, but is very familiar to many of you who have had a grant application turned down. So many centuries after the creation, it is unlikely that anyone could find hitherto unknown lands of any value. Spanish Royal Commission initially rejecting Christopher Columbus' proposal to sail west. Okay, so all that is to say that those of us who believe in physics beyond the standard model have history on our side. On the other hand, that new physics has been obstinate in not showing itself up until now. And I'm reminded of the Sherlock Holmes story, The Silver Blaze. So do people still read Sherlock Holmes? I mean, watching the TV program doesn't count. So you remember, Silver Blaze was a famous racehorse who mysteriously disappeared. So the stupid policeman in Sherlock Holmes, the policeman, is always stupid. Is there any other point to which you would wish to draw my attention? Holmes. It is a curious incident of the dog in the nighttime. But the dog did nothing in the nighttime. That was the curious incident. So, how would I interpret that? So I think that the fact that the dog has not barked tells us that we have an effective renormalizable field theory. Without the Higgs, without the top quark, the theory would not have been renormalizable. And if you try to calculate quantum corrections, you would have got infinities. And the fact that you don't get infinity, you get finite numbers, actually told us what the mass of the top, what the mass of the Higgs should be. The fact that the dog has not barked this time, I think tells us that we've got this renormalizable theory, and we have to look for something which goes beyond that particular renormalizable framework. So you can think of a couple of possible directions to go. One direction is to look for additions to the effective action which are non-renormalizable interactions, higher dimensional interactions. So I'll say a little bit about that. And another possibility is to look for some extended renormalizable theory, and that, of course, is where supersymmetry comes in. So let me first of all talk about the possibility of adding to the effective action higher dimensional operators. So I think with this audience, I don't need to sort of motivate this. You've already seen examples of higher dimensional operators appearing. So in the phenomenological particle physics community, there is currently a big industry of developing a systematic description of non-renormalizable corrections to the standard model Lagrangian, and then seeing how large their coefficients might be. Of course, since there are non-renormalizable corrections, they have coefficients 1 over lambda to some power. Here I've written 2 because effectively we're mainly interested in dimension 6 additions to the standard model Lagrangian. And the issue then is, how small could lambda be? This is, in fact, a question that was asked yesterday. What is the possible scale of new physics? This is one systematic way of trying to address that question. So here you are. So this is a list of operators that respect the SU2 cross U1 symmetry of the standard model. So you see, this is a somewhat complicated thing to study. There are terms which are purely bosonic. There are terms which are fermions plus bosons, etc., etc., etc. So I'm not going to discuss this in any detail. I just wanted to advertise that this is an interesting, I think, area of activity at the moment. There's a lot of open questions here in terms of, what is the best basis of operators to choose? How does one incorporate renormalization corrections, and so on. Let me just show you some of the possible effects that such operators might have. So what I have here is some examples of possible effects on Higgs decays. So we discussed Higgs decays yesterday. As I mentioned, up until now, if you average over all the possible Higgs production and decay modes, on average, it looks like the standard model to within 10% or so. But there could be discrepancies in individual decays at the level of 30%, maybe even 50%. So higher dimensional operators are examples of modifications of the standard model that could change some of the standard model predictions, those Higgs decays. So for example, up here, there is a scatter plot of Higgs into ZZ into 4-lepton decay versus Higgs into gamma-gamma. So I remind you from yesterday, those are the two decay modes that are perhaps best observed. Higgs into gamma-gamma may be a little bit above the standard model value. Higgs to ZZ looks reasonably consistent. And depending on which operators you add in, you can modify the standard model predictions in a fairly characteristic way. So, for example, you can get a significant enhancement of Higgs into gamma-gamma, and you can get that without modifying the standard model prediction for ZZ. So these different colors correspond to different possible operators. So if you look at this, you might say, well, you know, this black operator looks like a potentially interesting one to explore. Here's another example, which is Higgs into WW. And here on the vertical axis, there is a decay mode of the Higgs that hasn't yet been observed, Higgs into Z plus gamma. This is potentially a very interesting thing to measure, although it's going to be quite difficult to measure it very accurately. Here is, again, Higgs into ZZ versus Higgs into Z gamma, where you see that depending on which operator you add in, there's a whole range of different possibilities. So this is something which I think is going to be an active area in the future. And as I said, just in these two slides, I haven't been able to do it justice. This is another, sorry, yes. Yes, these operators all respect baryon number and lepton number. So if I flip back here, so for example, I've always got fermions appearing here in pairs, okay, say quark and anti-quark, right? So you respect baryon number. I mean, there's a whole other. Yeah, correct. So that was the possible effects on Higgs decays. There are also possible effects on Higgs production. And I mentioned yesterday, for example, the production of the Higgs in association with a W particle. And this actually is one of the observations that tells us that the Higgs has to be a scalar. Well, these operators can also modify the cross-section for W plus Higgs production, and they modify it in such a way that the cross-section increases at a different rate as you increase the energy. So one of the first things that I'm going to be interested in knowing about when the LHC runs at higher energies is the ratios of Higgs production cross-sections at high energy to what they are at low energy. And I mentioned yesterday the invariant mass of the Higgs plus vector boson combination, which, again, has told us what is the spin of the Higgs boson, but that could also constrain these additional operators. Okay, so that was just a mention of what might be the effects of high dimensional operators on Higgs phenomenology. So what else might be out there? So it's said on my T-shirt, and here I've written it in the largest possible font that will fit on my slide, supersymmetry. So I'm not going to go through all the familiar reasons why you might like supersymmetry. So I'm not going to mention grand unified theories. I'm not going to mention the fact that supersymmetry seems to be an essential aspect of string. I'm not going to say very much about the fact that supersymmetry could explain the dark matter. But I would like to emphasize two new motivations for supersymmetry that have been provided by the Higgs discovery. The first one, as I will discuss in a bit more detail in a moment, is that supersymmetry actually predicted correctly the mass of the Higgs boson. These other models, composite models, they could be adjusted in such a way that they are consistent with the measured value of the Higgs mass. But supersymmetry actually predicted it. And I'll discuss that and at least try to explain why in a moment. And another successful prediction of supersymmetry is that it actually predicts that the Higgs properties should be very close to the standard model values. And I'll come back to that quantitatively somewhat later. If you are a supersymmetrist, then you would not have expected so far to have seen any deviations in those measurements of Higgs couplings from the standard model predictions. So, in addition to all the other good reasons for liking supersymmetry, the Higgs discovery, in my view, has given us two additional reasons. And I think somebody asked me a couple of days ago, do you still believe in supersymmetry? And I gave back the answer, yes. And I said that actually I think that what the LHC has shown us so far, to my mind, relative to other possible extensions of the standard model, favors supersymmetry because of these two additional hints pointing in the right direction. Yeah.
As you were saying, suppose I'm looking for new particles, so I'll see some kind of missing spectrum or missing signal in some known experiment, So for supersymmetry in Ellis or somewhere, I see some kind of missing.
No, you don't. So that's why I said, the dog has not yet barked. Right? And supersymmetry is very difficult to see until you cross the threshold for producing supersymmetric particles. There are, of course, quantum effects due to supersymmetric particles that maybe you can see below threshold. And they could also, for example, generate dimension 6 operators. But those effects are relatively small. And that has to do with the fact that the particles within the standard model complete a renormalizable theory. So any other things, any extension of that renormalizable theory is in general going to have suppressed corrections. But no, so far there's been no direct evidence for supersymmetry. If there'd been direct evidence, I wouldn't be talking like this. I don't know why people say that. I will discuss this in a moment. Okay. Since I've talked about loop diagrams and quadratic divergences, I thought I would show this slide again, although it's somehow repeating what I was saying a little bit yesterday when I was talking about an elementary scalar particle. So I'm sure that nowadays you learn in high school that when you calculate loop corrections to a generic scalar particle, then you're going to get quadratic divergences because you've got a d4k over k squared. We're in 4 dimensions, remember, just in case anybody was confused. We're in 4 dimensions. So 4. Okay. And those quadratic divergences have the opposite sign for fermions and bosons. And so that leading quadratic divergence is cancelled out if you have a specific relationship between the scalar coupling and the fermion coupling. And this works at one level, one loop level, which is what I've shown here. But of course, it's a theorem that in a supersymmetric field theory, that cancellation of the quadratic divergences applies in all orders of perturbation theory. Okay, so, of course, when you cancel out the quadratic divergences, you are still left with a logarithmic divergence, a lambda. And that means that, for example, the masses of supersymmetric particles are logarithmically sensitive to, well, here's the cutoff, but you can rephrase that as being logarithmically sensitive to the normalization scale that you use. So that actually enables you to analyze the properties of supersymmetric models using the renormalization group, and I'll come to that in just a second. So I was talking yesterday about the renormalization of the Higgs quartic coupling, and in particular, this renormalization by the top quark. And I remind you that this top quark renormalization actually drives the quartic coupling negative at some scale, which is typically in the range 10 to the 10 to 10 to the 14 GeV. And I mentioned the fact yesterday that this instability could be cured by supersymmetry. Basically, what happens is that the stop counteracts the effect of the top, and so this blue term here disappears. So let me discuss that in a little bit more detail. And this is taken from a paper that I wrote with Douglas Ross about, I know, 10 or 15 years ago. I think it's amusing. So this dangerous renormalization of the Higgs self-coupling comes from the top quark, a fermion, right? That's what gives it the minus sign. So how do you counteract that? You want something with the opposite sign. That means a boson. So let's put in a new boson, and we adjust its couplings so that they're more or less the same as that of the top quark. And indeed, in that way, you can avoid this instability. So you might say, okay, fine. So let me not complicate my life with all those supersymmetric particles. Let me just put in just one little scalar which stabilizes the electroweak vacuum. The trouble with that is that then, in addition to the original Higgs quartic coupling, you've got other quartic couplings. You've got the 8 squared, 5 squared, you've got a 5 to the 4th coupling. And so you have to make sure that those couplings neither blow up nor collapse. And this is actually quite tricky to do. And as we showed, if you vary one of the parameters in the model by less than 0.1%, then you go from a situation where some coupling, as you run it up to high energies, blows up to where it collapses. Of course, that particular problem of the instability in the quartic coupling you can solve by introducing new fermions. But by the time you've done that, you've almost reproduced supersymmetry. So I wouldn't say that it's a theorem that the only way to make a completely safe theory that you can extrapolate up to the Planck scale is to make it supersymmetric. But, okay, I think certainly supersymmetry is the theoretically most appealing way of stabilizing the electroweak vacuum and avoiding these problems with couplings that either blow up or collapse. So that was a discussion of the quartic couplings in the theory. As I mentioned, in a supersymmetric theory, once you've got rid of those quadratic divergences, you've also got logarithmic renormalization of the mass parameters. And this is a picture which, in some particular model, summarizes the way in which those masses of supersymmetric particles get renormalized logarithmically. So here it's assumed that you have some model of supersymmetry breaking at the string scale, or quantum gravity, or something like that, that fixes boundary conditions at some high renormalization scale. And then you see what are the implications for low-energy physics. So what you see is that strongly interacting particles, like quarks, their effective mass actually tends to increase as you come to low energies. The same is true of the gluino. On the other hand, electroweakly interacting particles, like the photino or the bino, these tend to have smaller renormalization, even negative renormalization. Now, there is one interesting curve here, which is this one marked H. So this is the renormalization of the effective mass for one of the Higgs doublets in the supersymmetric theory. And what you see is that this is actually renormalized down to negative values. So cast your mind back to the first lecture. So in the first lecture, we had the effective Higgs potential of the standard model. We had a lambda phi to the fourth, and we had a mu squared phi squared. And I said, well, mu squared could be positive, mu squared could be negative. And in Subir's lectures, he basically had a model where you get this transition between the mu squared positive and the mu squared negative branch. But of course, you would like to have some mechanism for generating a negative value of mu squared. And here you have it. This logarithmic renormalization that you get in a supersymmetric theory could explain why it is that you get electroweak symmetry breaking, because the effective Higgs mass squared is renormalized to negative values. So this was actually an argument that was developed back in the 1980s. And in order for this to work, you need the top quark to be relatively heavy in order that this negative renormalization of the mass wins over the renormalization up here, which is due to the gauge interactions. And so some brave supersymmetric theorists actually predicted that the top quark should be very heavy, above 100 GeV, even before it was discovered. Okay, so what does supersymmetry have to say about Higgs bosons? It has a lot to say about Higgs bosons. It actually predicts a lot of Higgs bosons. It predicts that there should be 5 physical Higgs bosons. This comes about because in the minimal supersymmetric theory, you have to have 2 complex doublets. So in the standard model, you just have 1 complex doublet. That 1 complex doublet has 4 degrees of freedom. 3 of them are eaten to give masses to the W plus or minus and Z0. And so you've only got 1 degree of freedom, which is the thing that was observed on July the 4th, 2012. Probably. Maybe. But in a supersymmetric theory, you have to have 2 Higgs doublets. There's various ways of seeing the necessity of this. It has to do with the holomorphy of the effective superpotential, or it has to do with cancelling anomalies. Anyway, you need 2 Higgs doublets. So you start off with 8 degrees of freedom. 3 of them are eaten to give masses to the W plus or minus and Z0. And so you've got 5 physical degrees of freedom. So according to this, the particle that's been seen is one of the neutral scalar Higgses, and in fact there's 2 of them in the minimal supersymmetric extension of the standard model. Now at the tree level, it's easy to calculate the eigenstates of the Higgs mass matrix, and you find that the lighter one of these actually has a mass less than mz at the tree level. So back in the 1980s, when people hadn't got around to calculating the loop corrections to the Higgs mass, people were saying, well, surely you're going to find the lightest supersymmetric Higgs at the LEP accelerator that was operating at CERN in the 1990s. Unfortunately, some of us came along in about 1990, and we calculated the quantum radiative corrections to the mass of the Higgs boson. And these are actually quite important, and they tend to increase the mass of the lightest Higgs boson so that it becomes heavier than the Z. And that's illustrated on this slide here. So these different colors correspond to the different physical mass eigenstates. And you see that, well, 3 of them can basically become arbitrarily heavy. But there's one of them which is pretty much guaranteed to have a mass less than about 130 GeV. So this is what I was saying earlier on, that supersymmetry actually predicts the mass of the Higgs boson, the lightest Higgs boson, and it predicts that it should weigh less than about 130 GeV. So this is certainly consistent with the LHC. So most of the time when people interpret the LHC Higgs discovery in the framework of supersymmetry, they assume that what has been observed is the lightest Higgs boson. And as I said, there will be others, but they could be very much heavier. So this x-axis is actually the mass of one of the heavier Higgses. So as you increase the mass of that other Higgs, then the lightest Higgs remains essentially fixed. Okay. So if I go back to here, okay, so the horizontal axis is this parameter, the Higgs mass matrix. Okay. You would think that the mass of the lightest Higgs would depend on the parameter, but it turns out when you include radiative corrections that it's basically independent of that. So for larger values of tan beta, it goes up a little bit, but it basically saturates. Okay. For smaller values of tan beta, it can be somewhat different. But for other reasons, we believe that tan beta, this is kind of a lower limit on tan beta. I will discuss this in more detail in a moment. Okay, so this is the region where the lightest supersymmetric Higgs is what we're seeing on July the 4th. But notice that there is another interesting possibility over here where this green Higgs weighs around 130 GeV. And this green Higgs is actually the heavier scalar Higgs. And in this scenario, there would be a lighter supersymmetric Higgs, the red one, which the LHC experiments have overlooked. Or as I said, presumably what the LHC experiments have seen is the lighter scalar Higgs of supersymmetry. But it's possible that it's the heavier one, and it's possible that there is a lighter Higgs boson that they have not yet seen. So people, of course, have looked for these heavier supersymmetric Higgses, and this here shows you how the limit depends on this parameter tan beta. I guess I didn't define that. Tan beta is the ratio of the vector expectation values of the two Higgs doublets. So you see there's a big range of parameter space which has been excluded. So I mentioned that there's two different scenarios. One scenario where what has been seen at the LHC is the lighter scalar Higgs, and another one where it's the heavier scalar Higgs. So people have done analyses of the parameter spaces of supersymmetric models to see whether these are really consistent with the data. And this is the case where what has been seen is a lighter Higgs. And here you have things like the decay rate into vector bosons, decay rate into photons, and you can see that, for example, the decay rate into photons might be somewhat larger than in the standard model. So here's a similar analysis, but where what has been seen is a heavier scalar Higgs, not the lighter. And okay, here again, you can get regions of parameter space where the decay rate into gamma gamma is somewhat larger than in the standard model, and so on. So I think it's fair to say that you have to be slightly crazy to believe that what has been seen is a heavier scalar Higgs, and that there might be a lighter Higgs out there. But I do hope that the experiments will look very carefully at their data to see whether there might not be a lighter scalar Higgs somewhere hiding in the data. So the trick is that this lighter Higgs in this scenario would have a relatively suppressed coupling to vector bosons. So the search of the tevatron was production in association with a vector boson. Also, the searches at LEP were in association with a Z boson. So if you suppress that coupling, also makes it difficult to observe. Okay, so we haven't seen any evidence for supersymmetry yet. But what evidence have we not seen? So people have looked at precision electroweak observables, so detailed measurements of the properties of the Z and W boson. People have looked at the properties of B quarks, the way in which B quarks and K mesons decay. People, of course, have measured the Higgs mass. The one, if you like, piece of evidence for something beyond the standard model does actually not come from accelerators. It actually comes from cosmological dark matter. So we know that there is dark matter out there, and we also have an upper limit on the cross-section for that dark matter hitting regular matter. So this gives us a couple of interesting constraints. And of course, in answer to your question, the LHC has not seen any evidence for supersymmetric particles. It hasn't seen the supersymmetric particles, and as I showed on the previous slide, it also hasn't seen those heavier supersymmetric Higgses. So the fact that these dogs have not barked, with the possible exception of dark matter, gives us many constraints on supersymmetry. In particular, of course, the fact that this mass has been observed gives us some hint about what the supersymmetric mass scale might be. I'd just like to mention one accelerator measurement, which is a puzzle. And this is a measurement of the anomalous magnetic moment of the muon. So this shows a discrepancy with the calculation in the standard model. This discrepancy could be explained by supersymmetry. Initially, before the LHC started, people took that calculation very seriously, and they for that reason, thought that supersymmetry might show up in the early run of the LHC. Supersymmetry has not yet been seen. So now people are questioning whether this discrepancy in G-2, whether this is real. Maybe there's some mistake in the standard model calculation. Maybe the experimental measurement of the anomalous magnetic moment of the muon is wrong. Fortunately, a new experiment is now planned to redo the experiment. So maybe we wait for the microphone to show up.
I have an elementary question. When you say MSSM, how many parameters in the MSSM?
Okay. So if you say the MSSM, then basically only has one parameter, which is the mixing between the two Higgs doublets in the theory. Of course, when you try to construct a realistic model, you have to break supersymmetry. And then there's many possible ways of breaking supersymmetry. So that introduces many parameters. So in a moment, when I'm going to be trying to analyze the implications of those experimental constraints, I'm going to be working within one specific simple formulation of the MSSM with supersymmetry breaking in a particularly simple form.
And in this talk, you say something. This Higgs mass or something, 130 TIFR or something. Is that that's not depending on the, some suji breaking term, or is that the universal?
Well, as was the particular is the mass of the stop squawk. Okay, as you can see in this formula here. So in order to combine that constraint with all the other constraints, then what you do is you make some simplified assumption about the way in which supersymmetry is broken, so you can relate the mass of the stop squawk to other particle masses. Okay, so here shows you the limit within some particular simple supersymmetric model that you get from the non-observation of supersymmetry at the LHC. So specifically, people look for events where you assume that the dark matter is composed of the lightest supersymmetric particle that escapes from the detector, carrying away missing energy and momentum, and you look for events with missing energy and momentum in combination with jets and charged leptons. I think I discussed this in the discussion session yesterday. And here it's assumed that you have universal soft supersymmetry breaking. So in answer to your question, here it's assumed that you've got a universal input scalar mass m0 and a universal input fermion mass m1/2. And what you see here is those parameters must be larger than a few hundred GeV, a TeV, something like that. And that in turn means that the masses of supersymmetric particles such as the squark, the gluino, and the stop also have to be bigger than something like 1.5 or 2 TeV. So I'm participating in a collaboration where we put together all these various different experimental constraints, and we analyze what is the allowed region in parameter space. Here again, this is the scalar mass m0, this is the fermion mass m1/2. This particular scenario that we work in is something called the constrained MSSM. So the preferred region of parameter space is outlined in red here. The best fit is marked by this little green star. So the shift in the green star is the impact of the data taken at the LHC in 2012. But it looks like the LHC has really pushed you out to large values of masses. But in fact, the overall likelihood function is extremely flat. So it's true that the best fit is out here, but the overall likelihood function, as I said, doesn't really favor one mass over another. And in order to answer Sandip's question, the main reason why you're pushed up in this parameter here is actually this Higgs mass measurement. So back in the good old days of G-2, people thought we would be down here, but okay, Higgs mass is pushing you up there. So this is our chi-squared function, our likelihood function for the mass of the gluino. So the LHC tells you that the mass of the gluino is bigger than about 1.8 TeV, but it doesn't tell you very much about what the mass might be. So for reference, when the LHC is increased and when the collision rate is increased, you will get increased sensitivity to the masses of supersymmetric particles. And in particular, the sensitivity to the gluino mass will go up by something like a factor of 2. So there's a big region of parameter space which will be explored in future runs of the LHC. And this is something similar for the squark mass. Again, the lower limit from the LHC is somewhere around 1.6 TeV. And again, future experiments at the LHC should be able to push up to significantly higher masses. So I thought I had the stop, and I seem to have dropped the stop from this. But there's something similar, for the stop, although there the preferred mass is somewhat lower. It's about a TeV. Okay, so we've got this new particle. We haven't seen other new physics. We have various reasons for thinking that there might be other pieces in new physics. What next? What might you think of as the possible next big particle accelerator? I've already said that the LHC has very impressive capabilities for looking for heavier supersymmetric particles. It actually also could be very effective for studying the properties of the Higgs boson. In fact, the LHC, over the full history of the Higgs boson, of the LHC, will produce something like 100 million Higgs bosons. Of course, you can't observe all their decays, so people are also considering the possibility of building an accelerator which could measure with lower background the Higgs and perhaps observe more decays with higher precision. Anyway, this is what the LHC should be able to do. So the blue lines here, those correspond to the high-luminosity LHC that's now being planned. And you see that this will enable many measurements of the Higgs boson to be done at the level of 10% or better. So how might you measure the properties of the Higgs boson with higher precision? So one possibility is by colliding leptons, and there are ideas for linear colliders, the ILC, which would go up to 500 GeV in the center of mass, CLIC, which is an idea being developed at CERN, which could go to higher energies. There's also interest in building a circular electron-positron collider. And this is a project that I'm particularly interested in, something called TLEP, and I'll come back to that in a moment. And there are also people who propose to build a muon collider, although I think that technologically that's a lot further away. Okay, so what could these various different projects do? So here is another view of the likely accuracy attainable with the high luminosity incarnation of the LHC. So these are various different Higgs decay modes, ZZ, WW, and so on. And as I said, many of these can be measured with much higher precision than it's been possible up to now, even down to the level of a few percent. Now let me discuss this idea for a possible circular E plus E minus collider, which we call TLEP. We haven't quite decided what the T stands for. It could stand for triple because it's triple the size of the current LEP LHC tunnel, or it could just stand for T, tremendous, as in tremendously large electron-positron collider. So this actually is part of what I would consider to be a vision for the physics of the 21st century, particle physics, I should say, the 21st century, because the same tunnel which you would dig to accommodate TLEP could also be used to accommodate a high-energy proton-proton collider capable of getting up to 100 TeV in the center of mass, producing new particles weighing perhaps up to 10 TeV. And in fact, there's a working group which is now getting underway at CERN with collaborators around the world to study the possibilities of these machines. And I might mention also that our Chinese colleagues are developing similar ideas, although on a somewhat smaller scale. So unfortunately, with this projector, you don't really see it. You can probably see that little white circle there. That small white circle is the LHC, which has a circumference of only 27 kilometers. Here in the middle, that's Geneva. That's Lake Geneva coming down like that. And what we're thinking about is a tunnel which would be between 80 and 100 kilometers in circumference, which would circumnavigate Geneva. So the idea would be to put in that tunnel a very high-energy electron-positron collider and also eventually a proton-proton collider. So this shows you what collision rates you get in these various different ideas for an electron-positron collider as a function of their energy. So TLEP is shown here in blue. So it's limited in energy, but it gives you the highest luminosity. This green curve here, that is this other idea that's been developed at CERN called CLIC, which is for a linear collider which could go up to a high energy, potentially as large as 3 TeV in the center of mass. So you could consider two scenarios. Supposing that when you switch on the LHC at 14 TeV, you start producing supersymmetric particles. If you start producing them, then that's probably what you would want to study in a future accelerator. But very likely, they would be too heavy to be made in these machines, but they might be light enough to be made in this machine. So if supersymmetry shows up in the next 3 years, then this click accelerator might be the one that you want. On the other hand, if supersymmetry does not show up, and you have to focus on studying the Higgs boson in great detail, then I would prefer this machine over here. So this is a comparison of the accuracies with which the Higgs properties could be measured with these various accelerators. So the high luminosity LHC is in green. So you've seen these green lines before, but now the vertical scale has been expanded. And we've got these little blue lines corresponding to the ILC and the little red lines corresponding to TLEP. So I think this one plot somehow summarizes the Higgs physics argument for the TLEP accelerator. It would be, on paper, the most accurate way of measuring the Higgs properties. So I asked my student, Tivon Mu, to redo the analysis that I showed yesterday of this mass scaling of Higgs couplings. So this is the current form of this. So epsilon is, remember, this is the deviation from a linear coupling with mass. That deviation is currently at the level of a couple of percent. And this is what you would get with TLEP. So the error bars are completely invisible, and you would determine the overall scale of electroweak symmetry breaking with better than 1% precision. And you have to go down to the third figure after the decimal place before you start seeing a deviation from linearity. So this would be a wonderful machine for studying Higgs properties. Also, by the way, a wonderful machine for studying various other electroweak bosons, but don't have time to go into that. Okay, I think I'll skip that. So this is actually showing the potential impact of this. So these little stars here, these correspond to various supersymmetric model fits. And so they are the best predictions for the properties of the Higgs boson in supersymmetric models. And they deviate from the properties in the standard model. That's shown by the vertical dashed line. But they differ by typically a few percent. This is why I said in supersymmetric models, we would expect the Higgs boson to look very much like a standard model Higgs boson. And these horizontal bars, these are the measurement errors that you could expect with different accelerators. So you would want an accelerator which can tell the difference between those symbols and the dashed line. And you can see that TLEP, that's this red one here, this is what you would need in order to really be sure to create those supersymmetric models from the standard model. Anyway, like I said, we have to wait to see what the LHC produces at 13 or 14 TeV, because if it produces supersymmetric particles, you would want to go away and study those. But if it doesn't, then TLEP is maybe what you would want to do. How much more time do I have? I don't have any more time. Okay. So, like I said, beyond any reasonable doubt, the LHC has discovered a Higgs boson. And this is certainly posing an exciting challenge for theoretical physics. You know, the LHC at 13, 14 TeV will provide us with potentially another new exciting discovery. But if it doesn't, then we focus on the Higgs boson, and then maybe TLEP offers the best prospects. So that's what I wanted to say about accelerator physics. But I would just like to take out 5 minutes to discuss possible connections with inflation. Since there were lectures on inflation at the beginning of this school, I thought I would like to try some connection with that. So the cosmic microwave background certainly seems to be consistent with inflationary scenarios qualitatively. So there is this tilt in the spectrum of perturbations, which is suggestive that you're rolling down a hill. What has not been seen, another dog that did not bark, is tensor perturbations. And that's what you see in this picture here. So this is the amount of tilt, and the vertical axis is the magnitude of tensor perturbations. And you have to be down here below about 0.1. So although this is qualitatively in agreement with inflation, it is a challenge for simple inflationary models. And you can see here on this plot produced by the Planck collaboration, all these models which obviously have difficulties dealing with the data. But if you look down here, there is one model that is consistent with the data, and that is what they call here R². And this is actually an inflationary model which was proposed by Starobinsky back in 1980. So I'll say a little bit in a moment about the Starobinsky model. But the reason why I wanted to add this into my lectures is because you can reproduce the predictions of that model using the Higgs boson to do inflation. And you can also reproduce it using supersymmetry. And so I think there may be a connection between the Higgs and supersymmetry and these cosmological observations. So let me quickly run through this. So the Starobinsky model, all that you do is that you add to the standard Einstein-Lagrangian an R² term. An R² term with a coefficient 1 over m², and you have to make this coefficient large, which means you have to make m small. So you look at this and you say, well, you know, there's no scalar particle there, there's no inflaton there. That's actually not the case. You can make a conformal transformation, and then you find it is equivalent to a theory with a scalar boson. And that scalar boson has a very particular form of effective potential. And with that form of effective potential, you could then analyze the spectrum of perturbations. And this was first done by Mukhanov and Chibisov in 1981. And you get a prediction for the CMB perturbations, which, as you just saw, is extremely consistent with the Planck data. Now, Bezrukov and Shakhmashnikov a few years ago made the very interesting observation that you could basically reproduce the predictions of this favored Starobinsky model with the Higgs boson of the standard model. So here we've got the Higgs sector of the standard model Lagrangian. Here's the kinetic term. Here's the potential term. Here is the standard Einstein term in the Lagrangian, but with a non-minimal coupling to the Higgs boson and a coefficient psi. Now remember, I commented before that in the Starobinsky model, you need a coefficient of R² which is very large. The same is true here. In order for this scenario to work, you need that this non-minimal coupling here be very non-minimal. You need that this coefficient psi is much larger than 1. Typical values are of the order of 10 to the 4th. So now when you transform this to the Einstein frame, you get an effective potential which is almost the same as Starobinsky. Not exactly the same, but very similar. So this is an illustration of the potential. Over here, at large field values, it looks like Starobinsky. But of course, at small field values, it does not look like Starobinsky. It has this standard Mexican hat form. And this Higgs inflation model gives you predictions which are basically indistinguishable from the Starobinsky model. And that's shown here as these little green squares. Now, you might say, fine, why do we bother with complicated inflationary models? Why don't we just go with this Higgs inflation? We've just discovered a scalar particle. Maybe it can do two jobs. It can do electroweak symmetry breaking, and it can blow up the universe. But there are problems. And one very clear problem is that in order for this to work, you need this potential to be positive. But remember, I have emphasized that with a Higgs of 125 to 126 GeV, when you extrapolate the standard model potential to high energies, the quartic coupling goes negative. It's not positive, it's negative. So as long as we have this problem with the instability of the electroweak vacuum, it seems to me that you cannot do Higgs inflation. Now, of course, as we discussed yesterday, there is some uncertainty in this conclusion about the instability of the vacuum. Maybe people have misestimated the top mass. Maybe there is some way of saving Higgs inflation. But that, for me, is a big problem for the idea. So this is just reminding you of what I've been saying. And here you see explicitly that the Higgs self-coupling goes negative before you reach the scales that you would need for inflation. Although, if you played a lot with the uncertainty in the top mass measurement, maybe you could save the model. Okay, so that was Higgs inflation. How about supersymmetric inflation? So simple inflationary models require something that looks like an elementary scalar field. And in order to get the right magnitude of perturbations, you need a mass parameter for the scalar field, which is much less than the Planck scale, and or you need a small self-coupling in order to get the right magnitude of the perturbations. Now remember, delta T over T is the order of 10 to the minus 5. And of course, small mass, small coupling, those are things that are technically natural in a supersymmetric model. So 30 years ago, we argued that the natural framework for inflation was in fact supersymmetry. So last year, we discovered something truly amazing. We discovered that the simplest possible supersymmetric model actually gives you Planck-compatible inflation. So you take the West-Zumino model, as written down 40 years ago, and this model inflates. So I don't have time to go through the details of it, but there is a region of parameter space. Always in inflation, you postulate not just a potential, but also your initial condition. And there is a region of initial conditions where this potential gives you good inflation. And in fact, something that we're analyzing at the moment is the most general choice of possible initial conditions, and it actually looks even rather better than I've illustrated on this slide. So it could be that what the CMB is revealing to us is not the Higgs boson, but potentially it could be supersymmetry. And this is showing explicitly that the West-Zumino model gives you predictions which can comfortably lie within the region favored by Planck. So I guarantee absolutely the last topic. So, of course, if you believe in supersymmetry, you don't believe in some globally supersymmetric model like that West-Zumino model that I just wrote down. You believe in local supersymmetry, and certainly if you're going to discuss cosmology where gravity plays an important role, then you should be doing supergravity. So then you can ask yourself, well, what sort of mechanisms for inflation would you have in a supergravity model? So we discussed this specifically in the context of no-scale supergravity, which is the form of supergravity that you get naturally from string compactification. But that's another long story, so I won't go through that. So this is the sort of potential that you get out in this no-scale supergravity theory. So this is actually my second major epiphany of 2013. If you look at that black line, it sort of looks familiar. And actually, that black line is exactly the Starobinsky model. So this no-scale supergravity model spits out the Starobinsky model. And that model is, as I've just argued, compatible with the data and gives you a small value for the tensor to scalar perturbation ratio. Potentially, it could give you a small deviation from the naive Starobinsky model. So potentially, there's a whole area of what you might describe as Starobinsky phenomenology. Maybe the Starobinsky model is going to turn out to be the standard model of inflation, and maybe we're going to be into the business of checking whether this standard Starobinsky model continues to describe the data, and we're maybe going to be into the business of trying to see whether there's some deviations from this standard Starobinsky model. So that concludes my lectures, and I just wanted to conclude with this picture of the standard model particles, and I emphasized at the beginning of my first lecture that what you see on this slide was incomplete because it didn't have particle masses. I hope I've convinced you in these lectures that indeed we now know where the particle masses come from, and that there are every reason to expect that this mechanism for mass generation will be accompanied by other new physics that we may find either at a particle accelerator or with a big particle accelerator in the sky. Thank you.
Questions?
Yeah.
You know the Higgs, as you say, the constraints that imposes on SUSY particle masses. What is the story with G-2 then? You mentioned this in passing, but I didn't.
Yeah, so the quick answer to your question is I don't know. So it could be that there's a problem with the experimental measurement. As I mentioned, there is now a re-measurement that's being planned. It could be that there is some problem with the standard model calculation. Lots of people have looked at it. I haven't worked on that myself, but maybe there's something there that people have missed. Or it could be that we have to look for a slightly more cunning supersymmetric model. So I talked about this constrained MSSM with universal soft supersymmetry breaking masses. Maybe that's too naive, and maybe we should be thinking more about other ways of breaking supersymmetry.
Thank you.
More questions?
Supercell and Higgs in the supersymmetric model. So is it supposed to be very much heavier compared to the lighter Higgs?
Right. So there's an absolute limit, because I showed very briefly a search at the LHC, which typically gave a lower limit of, say, 200 or 300 GeV. But that depends on other parameters. So in our global fits, we find that it should weigh more than 500. But that, of course, is a model dependent state. It depends on the specific, simple mechanism for making supersymmetry that we discussed.
Thank you.
I'm sorry, I got a little confused at the end. Were you saying
That's
that?
not surprising.
Yes. Wondering if you were saying that the Higgs is actually the inflaton which is causing inflation. Is that the idea, or?
So that was the idea, but I don't think that idea works. Because in order for that to work, you need positive potential. If you extrapolate the standard model up to high energies, then it looks like the potential goes negative. So for that reason, there are other objections to Higgs inflation. For that reason, I don't think that Higgs inflation works. But there is a footnote. The footnote says this conclusion that the Higgs potential in the standard model goes negative is not absolutely sure, because it depends in particular on the uncertainty in the top quark mass. So our experimental friends should measure the top quark mass as accurately as they can, so that we can be sure whether that effective Higgs potential goes positive or negative.
Anything else?
So when you said you had R² term for the inflation, so you did not. That was R plus R² term was giving you all the prediction without the inflaton.
So the Starobinsky model is equivalent to a model with an inflaton. You can write it in different ways, whether in the Einstein frame or the Jordan frame. If you go to the Einstein frame, then you get, in addition to, you get this scalar, okay, and this scalar is an inflaton. This is somewhat of a frame-dependent interpretation. The physics is clear.
Anything else?
I think everybody wants their tea.
So, well, if there are no more questions, we will. Yeah, sorry, you did say it. But I want to lead up to, so you should have said it. Well, we will, of course, thank John again. But then there's. But let's not disperse, because here we have this momentum for John. And I'm going to, which is the Konark wheel that we have all seen. And I request Anshuman Maharana to please present it to John on our behalf.
Okay. Okay, thank you very much. Just like the central part of one of the LHC detectors.
Oh,
Okay, thank you very much.